Welcome to GO164. I've put together this presentation to assist you in completing the practical exercises outlined in your practical manual. I would appreciate any feedback as we proceed. I'm hoping to complete a series of these presentations during the session to assist you in getting the most out of this subject. That said, this presentation should be used in conjunction with the practical manual along with your own background reading. To get started, I thought it might be useful to cover some of the basics about topographic maps, as well as a little historical information. Okay, so what is a map? A map simply describes a set of features and can be displayed either in a digital format or in a hard copy, typically on paper. Some of the themes that they cover can include things such as topography, geology, political aspects, economic or resource type maps, or even just a simple road map. The term we use to describe these maps is typically thematic maps, one that shows a particular theme. All maps are a generalized view of an area, typically scaled down to show features of interest and designed to be displayed in a usable format. In this subject, we're going to focus on topographic maps, but in our modern mapping environment, we can create many different types of maps and analyze the data that makes up the maps using computer-aided software such as geographic information systems. More on some of this as you proceed through your degree. In fact, there is a trend now to store vast amounts of information that has location attributes so that we can query and investigate particular themes pertinent to our management of resources and infrastructure. These might include things like vegetation and soils, or infrastructure such as pipelines, cables, and various other assets. So one of the things to consider in any map is the scale. The scale is typically a ratio of the map units to ground units and is usually represented by a scale bar, a linear scale bar, or a unit of measurement or some form of statement expression of scale. Likewise, most maps, or at least the paper ones, are usually flat. We know our Earth is round, and therefore to get to a flat map we have to transform that round Earth into a flat surface. The process that describes this is known as projections and is essentially a mathematical process that we need not be too concerned about in terms of the maths, but we should understand the effects of the projection on the map. More on this a little later as we go through our presentation. Okay, so we all know that the Earth is round, or more correctly a squished sphere, but how do we know that, or more importantly, how did we recognise that? Obviously in the modern world we have access to satellite imagery and lots of pictures that we can see of the Earth, but in historical times it took the work of some amazing philosophers to deduce that the world was round. Remember, originally people thought the Earth was flat. Seems silly now, I know, but they didn't have access to the technology we have today. So one of these philosophers, Aristotle, through the process of deduction and logic, noticed that the Earth's shadow during a lunar eclipse produced an arc on the surface of the Moon. This led him to believe that the Earth must be round rather than flat because of that picture that he could see on the Moon. Like Aristotle, many of the other creative thinkers of the time had watched ships as they disappeared over the horizon. They noticed as the ships moved further away that they didn't just get smaller in the distance, but rather the front of the ship disappeared with the last thing to be seen the tip of the mast. Therefore, they suggested that this was very similar to objects that went over a hill and deduced that the Earth must be curved for this phenomenon to occur. So over time, the flat Earth thoughts were dismissed and a round Earth was accepted. Various philosophers then started asking questions about the size of the Earth. Eratosthenes, a philosopher, set out through deduction to estimate the size of the Earth. He had been told by travellers that during the summer solstice, the longest Sunday when the sun is at its most northern position in the sky, that the sun's rays shine directly to the bottom of a well in a town called Cyan. He deduced that the sun must have been parallel to the well for this to occur, but he had also noticed that at his location in Alexandria, the sun was never directly overhead. In fact, he noticed that a shadow was cast from a perpendicular pole called an obelisk. So Eratosthenes measured the shadow cast to be around 7.2 degrees. Using the work of Pythagoras, he made an estimate of the Earth's circumference and got a figure around 46,000 kilometers. This was pretty good, given that using our modern measurements we know the Earth is to be approximately around 40,100 kilometers. So how did he do this? The next slide shows some of the details, but essentially knowing that the shadow was 7.2 degrees and noting that that was approximately 1/50th of the circumference of a circle, he simply calculated the distance between Alexandria and Cyan and multiplied that by 50. The distance between the two cities was 5,000 stadia, a Greek unit of measurement which was approximately equal to 185 meters in our modern day measurements. Therefore, 5,000 stadia times 50 was equal to around 250,000 stadia, or approximately 46,250 kilometers. Obviously, in our modern world, we have access to GPS and a range of far more accurate surveying equipment that allows us to calculate the shape of the Earth, the movement of continents, and to accurately position ourselves on the Earth's surface. The study of the Earth's shape and surface is known as geodesy. Okay, so enough on some of the brief history. Let's talk a little bit about location. There are many ways to measure location, and the most widely used system, or at least historically, is that of longitude and latitude. This system is typically referred to as a geographic coordinate system. Latitude is defined as the angular distance north or south of the equator measured from the center of the Earth. It is expressed as an angle, and the lines that define latitude are known as parallels. We can see that when we look at this diagram, the equator is defined as 0 degrees, with the parallels going northwards and southwards to 90 degrees as they reach the poles. The lines run east-west and parallel the equator, hence the term parallels. While a geographic coordinate system is useful, particularly for navigation, it is somewhat cumbersome to use and hard to measure. Coordinates are typically expressed in degrees, with 1 degree equal to 60 minutes and 1 minute equal to 60 seconds. Latitude can be easily determined by reference to the stars and the sun's position in the sky, methods dating back to ancient times and often used by sailors. The angle of the sun above the horizon indicates the observer's latitude after adjustments for both the time and the seasonal Earth tilt. At night, fixed stars are used again by examining the angle between the position of the star and the horizon. In the northern hemisphere, Polaris, the northern star, is used, whereas in the southern hemisphere, Polaris cannot be seen, so the Southern Cross is used instead. To pinpoint our location using a geographic coordinate system, we also need to know our longitude. Longitude is defined as an angular distance east or west of a point on the Earth's surface. The lines run north and south, and the line connecting common points is called a meridian. Meridians are at right angles to all parallels or latitudes, which makes this system extremely useful for navigation. The 0 position or 0 degrees is known as the prime meridian. The prime meridian passes through the Old Royal Observatory at Greenwich in England. The diagram on this slide shows how the meridians are divided around the world. Longitude is much more difficult to determine the location of using the stars or sun because the Earth is constantly spinning on its axis, making the reference of the stars appear to move relative to the Earth, or more correctly to the person that's actually viewing them. We can also produce other types of maps, such as this one that shows us how natural environments differ dramatically from the equator to the poles in both their process and appearance. These differences result from the amount of solar energy received, which varies by latitude. The amount of energy received at different latitudes and depicted by the seasons is controlled primarily by the Earth's spins and its inclination as it revolves around the sun. As we can see in the diagram, much of our weather and geographic systems are driven by the amount of solar energy that a location receives at a particular latitude. Okay, so back to projections. As I said earlier, to take a round Earth and make it into a flat map, we need to use a mathematical model so that we can project the surface onto our flat map. We aren't concerned in this subject about the mathematical models, but we should be aware that any mathematical model is going to distort some aspect of the round Earth as it is projected onto a flat surface. Typically, distortions are introduced to either the shape, area, distance, or direction during this process, and therefore it is important that the right projection is used when looking to preserve any of one of these particular features. The diagram here shows a number of projection models, so let's take a little closer look at some of the effects of these projections on the next slide. Okay, so here we have the Mercator projection, a commonly used projection for many mapping applications. So one of the issues with the Mercator projection is the distortion of area, particularly towards the poles. If we look at the grid lines, and if we follow the grid lines north and south, we can see they become elongated as we reach the top of the page. Obviously there is some distortion occurring, or we would expect the grids to remain constant. A classic example of area distortion is if we look at Greenland, indicated by the red arrow, relative to Australia. Now Greenland is about 1/5 the size of Australia, but in this projection Greenland looks significantly larger, caused by the area distortion of the mathematical model used to create the Mercator projection. Another thing that is distorted in this projection is distance. Again, using this example on this image, if you wanted to travel from Portland, Oregon on the west coast of the US to Cairo, I'm not sure this is a popular travel route, but anyway, on the map the shortest distance one would think would be the direct path as indicated. That isn't quite right. In fact, the shortest distance is to follow the Great Circle, again indicated by that red arrow. So if you were travelling by air, it isn't the pilot taking you on a scenic route of the Arctic Circle, rather they are conserving fuel and travelling the shortest route. This makes sense when you think of the globe and the fact that it shrinks towards the north and south poles. Therefore, travelling this route is always going to be shorter because we're going to cover less distance. What about direction? Well, because the grid lines are at right angles to each other, direction is usually preserved, and therefore the Mercator is useful in navigation applications. So, the Mercator projection is good for some things, but it doesn't show areas well, at least not at the scale shown here, and not towards the poles. Certainly towards the equator we can see that the squares are much more uniform, so areas around the equator are likely to preserve area much better. So if we wanted to conserve area, we would need another projection. So let's look at that on the next slide. So here we have the mole-wide projection. This projection is known as an equal area projection, and the mole-wide projection is one of the most commonly used projections when we are interested in preserving area. Now again, if we examine Greenland versus Australia, we can see that now Greenland appears to be about the right size and a lot smaller relative to Australia, like it should be. But the lines of longitude and latitude don't intersect at right angles everywhere on the map. They do at the prime meridian, the line of 0 degrees longitude that passes through Greenwich Observatory in London, but you can see elsewhere the longitude lines are shown as curvy, and so therefore we have some difficulties with determining direction. Likewise, as we approach the edges of the map or edges of the projection, we tend to get some distortion of shape. So while this projection is good for areas, we tend to get some other aspects being distorted. There are a myriad of other projections. For example, on the next slide we could slice up the map a bit like spreading out an orange peel, and in that way we could show particular areas of interest. In that example the continents are shown, but equally we could focus on areas of the ocean if we wanted to produce a map of them. So that's just a little bit on projections to give you the idea that any map projection does involve some distortion, and that goes right down even to the level of topographic maps we were looking at, and I'll show you that in the next slide. The important thing I want you to get out of this is that it is important to understand that projections does influence a number of aspects when mapping, and this is particularly important when collecting data using handheld GPS, as you typically need to define your projection and datum prior to collecting the data. Obviously, if you intend on merging the data with other data sets, then you also need to take this into account prior to collecting data so that they're all using the same projection and datum. Okay, so I've got the Perisher map here. So Even though our topographic maps only occupy a relatively small part of the Earth's surface, the distortions aren't particularly large on any one of these maps, but there are still some there, and it's useful to take a look at these just so you're aware. So if we take a look at the right hand side of the map, we can see that the edge is along a line of longitude. It is at roughly 148 degrees 30 minutes east, and I'm using, as I said before, the Perisher map here for this example, but if you look at the Wagga map you can see a similar thing. So all the maps in Australia are cut up in terms of longitude, and we could use longitude and latitude to give a map location, but these geographic coordinate systems are typically cumbersome. As I said earlier, if we wanted to give the locations, we would have to give it in degrees, minutes and seconds, and these are hard to work out and don't tend to mean as much as meters when we're out in the field. So therefore we've used a much more logical system, and most countries have adopted that system to a map grid system of their own to give them a simpler way of locating themselves. So on this map we can see a set of grid lines over the map, and these relate to the Australian map grid. Anyway, a bit more on that later about map grids, but if we compare the most easterly grid line to the edge of the right hand side of the map, we can see that they are not parallel to each other. The grid line is closer to the edge of the map at the bottom and diverges as we go northwards towards the top of the map. And that is just showing that there is a bit of distortion between the grid lines that are meant to be north-south and the lines of longitude because of the resulting projection used, in this case the universal transverse Mercator projection that is used on a lot of Australian map grid maps. The only place that the grid lines and the longitude lines coincide is the centre of the mapping zone, and I'll talk a little bit more about this in a little bit more detail shortly. Okay, so that's a little bit of background about map projections, and it's important that you know a map is based on a projection and that you need to be aware that there is always going to be a little distortion involved. Okay, so before I talk about locating ourselves on the map, let's talk a little bit about scale, as this relates to the first part of your practical exercises. If we want to interpret the size of something on the map, or if we want to measure distances, then we need to know at what scale the map is. So the scale just tells us about the relationship between distance on the map to the distance on the ground. We can express the scale in different ways, but it's important to have an understanding of how these relate to each other. Now, typically scale is expressed as a ratio or representative fraction, as illustrated in the diagram, or quite often it is put in the form of a statement, particularly when we're discussing this with colleagues. Or it can also be shown on the map using a linear scale, such as a scale bar, to make it easy for us to measure between points on the map. So if we take a look at the Wagga map or the Perisher map, we can see that they both have a scale bar and a ratio or representative fraction. And if we take a closer look, we can see that 1 centimetre is equal to 25,000 centimetres, given by the ratio of 1 to 25,000. Also, if we look, we can see that the grid squares on the map are 4 centimetres, and that 4 centimetres is equal to 1 kilometre, given the ratio that's defined on that particular map. Map ratios or the representative fractions are unitless, so we could use whatever units we wanted. For example, if we were trying to be very precise, we could use millimetres, but the same units must be used on both sides of the ratio. We can obviously convert those units to other units that are more meaningful. So the first part of the practical is to get you used to map scale and converting units to something more meaningful, as I've just done when discussing them. Another important thing about scale is how the terminology is used. For example, as cartographers or geographers, we tend to talk about a large scale as being one that covers a detailed area, but it usually encompasses quite a small area. Ecologists often describe a large scale as a large area or a large study area. This means the opposite, and therefore it's important to understand what we're talking about when we discuss scale with our colleagues. In the example I just used, an ecologist would refer to a large-scale study as covering a large area, where we would interpret their meaning of large scale as covering a small area in more detail. Okay, so let's look at some of the questions on scale. So the first question in your practical exercise asks you to convert the following scales to a representative ratio. So if we look at question 1A, it asks us to convert the scale of 1 centimetre to 500 metres to a representative ratio. The first step is to make sure we are working in the same units. So let's stick with centimeters. So we know there is 100 centimeters in a meter. So to convert 500 meters to centimeters, we simply multiply 500 by 100, which gives us an answer of 50,000. So in answering question 1A, we would simply write the ratio as 1 to 50,000. So for question B, it should be relatively simple, knowing that there's 100 centimeters in a meter and 1,000 meters in a kilometer. For question D, I've used miles, and I've done this on purpose, as whenever you look at older maps, particularly when looking at historical maps, say prior to the 1960s, they use an empirical scale of inches and miles, so it's useful to know how to do the conversion. In our case, if we look up how many inches in a mile, you'll find that 1 mile is equal to 63,360 inches. So given that we have 4 miles, we simply multiply 4 miles by 63,360 inches, remembering that we want to keep the units the same on both sides of the ratio, and given that we've got 1 inch on one side, we'll stick with inches. So the ratio for that particular question becomes 1 to 253,400 inches. So that should get you through question 1. For question 2, we are simply doing the reverse, taking a ratio and converting it back to a statement. However, we want the statement to be something meaningful. So again, if I said let's walk 25,000 centimeters, most of us would look to each other saying, how far? So it is therefore useful to convert the statement to something more meaningful. So rather than saying 25,000 centimeters, we would say 1 centimeter to 250 meters. So for 2A, we would convert the ratio using the same convention we just used in question 1. So given that the ratio is 1 to 250,000, or 1 centimeter equals 250,000 centimeters, and since we know that 1 centimeter equals 0.01 of a meter, or to get that we just simply divide 1 by 100 centimeters, because we know there's 100 centimeters in a meter, we can then calculate how many meters in 250,000 centimeters by simply multiplying 250,000 by 0.01. So this equals 2,500 meters. We could further rationalize that down, because 2,500 meters, although that makes sense, isn't the simplest way of turning that into a statement. So we know that there's 1,000 meters in a kilometer, so therefore there's 2.5 kilometers to 2,500 meters, which would be more meaningful. So simply dividing 2,500 by 1,000 gives us 2.5. So your statement would read 1 centimeter for 2.5 kilometers for question 2A. Based on this information, you should be able to do the remaining questions for question 2. For question 3, you are asked which is the larger scale. The larger scale is always the larger fraction. An easy way to think of the larger fraction, if it's not obvious to you, is to think of an orange. If we were to cut an orange into 25,000 bits, those bits would be larger than if we were to cut the orange into 50,000 bits, which would produce obviously smaller bits. Therefore, the larger fraction is 1 to 25,000. I've already explained what is a larger scale to a geographer, so that should be sufficient for you to be able to answer the second part of question 3. For question 4, you should now have the skills to calculate the width of the road given a ratio. Obviously, depending on the scale of the map, if the road was drawn at the correct scale, the line could either be quite thick or very thin, depending on that particular scale that was used on the map. You should see that there is a difference between the measured width of the road at the two scales, and while at 1 to 25,000 the road width is feasible, certainly at 1 to 250,000 our Australian roads are definitely not that wide. So this exercise on scale was just a little example to illustrate that map features are not always drawn at scale, but typically you should recognise by now, particularly when looking at the legend, that map makers use a standard set of symbols to represent features on a map, with some of these drawn to scale and others that are not. For questions 5, 6 and 7, you're asked to measure distance. This will take a little patience to find some of the locations. Obviously, if we had a way of locating features on the map, the process of finding bridges and railway stations would be a lot easier. And that leads us into the use of a map referencing system. We'll come to that shortly in the next section. While I suspect many of you will not have access to a map wheel, they are certainly a more efficient mechanism of measuring distances, particularly when the distance isn't a straight line on a topographic map. For the exercises, you certainly don't need to buy one, but it's good to know that they exist. Finally, for question 7, you are asked to calculate the sinuosity of the river by measuring the river length and valley length. Sinuosity is a ratio and therefore, again, a unitless measure. Geomorphologists typically use sinuosity, or use the values measured by sinuosity to describe the shape of the river, with a typical value for meandering rivers being a value of 1.5 or greater. In our case, it's a little higher, as you'll work out when you do your calculations, and we can see that in the case of the section we have measured, that the river is fairly curvy or bendy. If the river was dead straight, it would have a sinuosity of 1, i.e. the river and valley lengths would be identical. Okay, so that covers the first few questions in the practical, and in the next presentation I will explain how to locate features using a map reference.